All right, cool. Hello, everybody. It's great to be in Jamaica. My name's Joir-dan Gumbs, as he said. I work at IBM Cloud, and today my talk is going to be on DIY, do-it-yourself serverless with Python3 and Docker. So. Be able to build applications around that can grow with your company or with your project or what have you. And the integrations tended to be relatively difficult at times, right? So we started wrapping ourselves around standardized formats, whether it's JSON or SOAP, if you can remember SOAP from way back. I think people are still using SOAP now at some places, right? So the standardization helped us be able to compose newer applications because, hey, I know what that data, what the data looks like coming out of that. You may have seen certain patterns such as the enterprise service bus. That was the integration layer for all of your different applications, right? And from a business standpoint, many of the application interfaces didn't provide the requirements for newer applications. Or maybe the data that was coming in was across multiple systems. So you were required to build out your enterprise service architecture in a way that could relatively easily pick out what it was that you needed in order to build what was next. So here I've got my little old application here, and I've got a cat who's looking for food. And the idea is that the cat presses a button and the food is prepared for it through, whether it's cooked or dry, whether you need to fry something up or what have you. The cat presses a button and food's supposed to come out. It's got a really old name, OMatic. I couldn't really think of a good name for this thing. But the application is responsible for taking the order when the button is pressed. It's responsible for getting ingredients. It's responsible for cooking the food and plating the food. And it's a lot of functionality. If you can remember, code bases in this model tended to get very large, so they're quite unwieldy at times. Any change or update required or revision to the application as a whole, any bug or crash could bring the entire system down. So if the order didn't take, yen or something, and it was only for US dollars, and then that crashed, that's not really a good reason for all cooking to stop. It's not a really good reason for getting ingredients to stop, right? So because these were so monolithic, we decided that we were, as time progressed, it was a better idea to break these things up into smaller services that could be easily utilized. So that's where we get into microservices, right? So idea of microservice, you decouple an application to smaller components, fundamental components, and expose those functions as a standard accessible interface is kind of the same way that we were trying to do so for service-oriented architecture. So you can already kind of see that where service-oriented infrastructure was focused on enterprise scope, bridging together multiple applications in order to get whatever products you were trying to build out to communicate with one another. This is more focused on that application level, right? So we're trying to get the services that compose an application to compose themselves to build out said application and build newer applications around it based off of those components. Microservices typically, they're developed with kind of I call it a full stack isolation of business function, infrastructure, and system of record, which is like your database. When you have a microservice, a lot of microservices have like their own small specialized database that holds information that's key for that service to be done. They're all hosted maybe on separate instances, run in separate containers if you want to think about Docker and things like that. I'll get into all of that. But the focus here is on agility, flexibility, scalability, and resilience. So when you're building with smaller code bases and you've got different teams working together, they're able to build out these services separate from other components of a team. So if a new feature comes in, let's say, give an example for like the cooking aspect of our application. If we weren't handling deep frying, and now we want to handle deep frying, well, the team that's responsible for that code base for that service can build that up without even having to worry. They can build it, they can test it, and they can deploy it without worrying about taking orders or without the ingredients or what have you. And then as the other teams get the requirements ready so they can handle those scenarios, they can build them in on their own timeline without having to worry about what your timeline is. Let's see. These things can be, I'm kind of a big fan of Python, but microservices can be built in multiple languages, Python, Go. They provide the flexibility because you can deploy each component of those services across multiple availability zones on different types of hardware, and they can, when you put the proper checks and balances in place, ideally they should be able to fail without harming unrelated functionality of an application, as I had said before. So as I switch over to here, we took that big, food application that we were building, and we've kind of broken it up into smaller services, as you see here, as I mentioned. Ordering is its own service, recipes are their own service, ingredients, tools, so if you wanted to get like a blender or you want to get like a mixer, service that handles the process for getting those things out, cooking service and preparation service. It's not really realistic, but it's kind of was an easy way, at least for me, to visualize it when I was trying to understand a lot of these things. And if you note, there's two different barriers that you can see, right? There's the enterprise barrier that signifies that within my enterprise scope, I've got a bunch of different applications that are communicating with one another in order to provide value and services. So maybe my payments application is still old, and I don't have the wherewithal or the time to refactor that out into microservice architecture, but my ordering service still needs to be able to handle payments. I can still do that because there's proper, if I was done in a service-oriented, if a services architecture, I should still be able to interact with that application based off of the endpoints that have been provided by that application. Sorry, a lot of talking. So yeah. But the downside, there's a lot of benefit here, as I said before. But if you notice, there's a lot of duplication going on here. For every microservice that you create, there's infrastructure that has to be instantiated. There's server code cruft that you have to build out. How do you open up whether you're opening up ports, whether you're handling a bunch of different endpoints for your web service or what have you. And maybe you don't have that much business logic or business functions that you're trying to expose as microservices. So maybe this might be a little bit too much in terms of upkeep and maintenance and manpower to formulate teams to be able to do all of these things. So then we can enter into the conversation of serverless computing. So serverless computing is a service hosting model that abstracts the network and compute infrastructure required to provide that service, right? It's also known as, to some people, as function as a service, because in this case, your key deliverable is that business function that handles the logic. So maybe if I'm taking orders, maybe I just have take order and process order as my two services that are exposed. If that's the case, then maybe I don't want to have the build out the infrastructure for all of that. I just have the logic in place that I want to be able to access those endpoints and grab it out. I just have functions, right? So I can write stateless decoupled functions and upload them to some form of a serverless platform. The functions then can be accessed through REST or WebSocket connections that are triggered either through event hooks. Let's say I want to update something on GitHub, and on an update it does X, Y, and Z. That can be a stateless trigger that kicks off some process on my serverless function, right? Or the cat pressing the button on the box to get its cat food because it's hungry in a Pavlovian kind of way. Those are all things that can trigger out these events. And they can also be utilized in the same way that API endpoints can be used, right? This isn't chosen as a performance decision, but you can see it more as an operations decision based off of certain use cases. If you're trying to do something highly performant, maybe it might not be the best situation for you to be using serverless. But if it's something small and quick, like, hey, I've got data, I want to be able to see how large the file is or what have you, that might be a great use case for it. So it's all based off of what it is that you're trying to build, right? So we can look at the same architecture that I had before in terms of microservices, and you'll notice that a couple of them I've changed out to just being serverless in themselves. It still looks like kind of a similar breakdown as the microservice one, but if you notice there's no server code. There's still a database somewhere that you're connecting to for some of these services. That doesn't really go away, but no longer are you trying to have to maintain and manage the instance that you've instantiated to run the service. No longer do you have to write out a bunch of cruft code in order to get the servers up and running, provisioned endpoints or what have you. Your provider typically is the one that'll be able to handle out your API economy of scale and things like that. There are a couple platforms that are out and about right now. Google Cloud Function, AWS Lambda, Azure Functions, and I work at IBM, so I have to say that we have ours as well, and this isn't a sales pitch or anything like that. But there are many different ones. If you haven't tried out serverless, it's definitely something that it seems like it's up and coming, and depending on the use case, might be a good thing to pay attention to for what next project that you're building. So why would I build my own, right? Like, why not just work on the one that we have at our company? I like building stuff. I mean, it would be like the nice and easy thing to say, right? Like, but truthful of the matter is that one of the core things that I do at IBM is we try to keep ahead of what's going on in the field, right? So many times there are certain features that are coming out for different areas of computing that it might not make sense for me to jump into the big, large code base that we have if I'm just trying to mess around with a couple small different features. So sometimes I build out stuff myself to kind of get an idea and understanding as to how things work from whatever it is I'm looking at. So this was one of those projects where it was kind of like a labor of like painful love in the sense that I'm in a new area, I'm trying to build out this architecture, I don't really know what it is that I'm trying to do, but I know that in order for this to work, I need to have a function that can then run without the person that's providing me the work, the business logic, to be able to run it without thinking about managing it. That should be on the provider side, right? So that's kind of like the TL. That's like the long version of why I did it. But really, I like building stuff, and it's cool, and I like Python. So Python, building out architectures is a lot of fun. So there's a couple of things that I needed to think about when I'm trying to build out my own serverless platform. First of all, I needed to understand how serverless actually works, right? So a very basic understanding, this is very basic. There's a lot of other things that go into play, but you have a trigger that activates that then hits some serverless engine. The serverless engine or action engine or whatever you want to call it is the primary driver of which will run the functions that have been provided to me by my customers, right? the engine will, if I'm running there's typically a URL or something like that, or some application that'll run this, and it will say, I want to run function ID of 1002. So the serverless engine's responsibility is to go check in the action registry, which is the registry of all the functions that have been provided to me by my customer, and find that action in the database or whatever repository that I have. From there, the serverless engine then is supposed to kick that task off and monitor it. If you're looking at it from a large provider like Amazon's AWS Lambda or IBM Bluewisk or Google Cloud Function, there's a bunch of metering and monitoring and rate limiting and a bunch of other things that happen around this time to see, can I run this function? Do I have the space to run this function? Where should I run this function? How much should I charge the customer for running this function? Among other things. But for the most part, I only really care about running my function. So action registry, grab the function from the action registry, and then run the action. So if you see number 3, I'm running some number of functions, and as I'm running those functions, I'm taking a look at whatever that output is so that I can return it back to the user that's requested a response from the trigger. All right. Ooh, sorry. From there, I started to think about what like a very basic platform architecture would look like. So I still have my trigger. It needs to be able to go through some sort of router, because if I'm thinking of this from a grander scale, I may have action servers running all over the place in kind of a microservices kind of way. Right? It all kind of ties itself together. From there, I'm going to try and hit like some container host. Many of these services tend to utilize containers in order to run these functions because it's a great way to isolate themselves from other people's functions. Last thing you want to have is a situation where if I'm running a Python3 function that I wrote and somebody's got Python2, 2.7, I don't want there to be collisions when I'm running functions, because then I'm not going to be able to get what it is that I want. Docker provides itself with a lot, containers, I say Docker, but containers provide itself with a lot of functionality that enable you to be able to quickly bring up and tear down resources. So it's very useful for driving functions, especially if you've well-defined your function in the container. The function registry is very much the action registry, and I keep changing out the name just so that we kind of get the parallel that an action is a function, and a function is an action in this case. But this is very similar. It's tied to the container host, and it's on a deeper level, it's where all of my images that comprise my functions are stored, right? There's a cert volume that's there in order to make sure that I'm securely when you're talking, there's securely communicating with the container host and being able to get results from all of the functions that are currently running based off of what event was triggered. Right. Yeah. So that's cool, but why would I use so I did this in Python using Python3. I'm a big fan. If you haven't switched over yet, I suggest that you start switching over. The tide is starting to get a little bit higher, and it makes a lot of sense to do so. But I believe that it provides Python and Python3 provide a lot of great tooling and resources in order to do a project like this very well and easily. So Python in general, as we all may or may not know, is great for rapid prototyping, and I believe it's great for writing microservices because you can write clean, readable code quickly, right? So if I want to test something out, it's very great for doing something like that. But one of the key things that I really like is async I/O. And I know that there was a talk, training session yesterday that may or may not, I believe we didn't really get too much into async I/O, so I tried to change this up a little bit so that we would be able to cover some of the key pieces for that. But it allows you to write scalable event-driven code. As we're dealing with events in a lot of cases that are triggering the triggering the start and ending of a lot of these functions, it makes a lot of sense to utilize the async I/O to build out nice event-driven services. AOHTTP, which I use, builds on top of that, so you can build out these scalable web services, namely the action server that I'll be going through very soon. There's a lot of other cool things. There's a lot of other cool things that Python3 has, and because this is like a time-limited presentation, I suggest you check that out. I put a link there, just take a look. But async I/O, more in detail, provides infrastructure to write concurrent code. Utilizes an event loop of which you schedule tasks on there. So multiple functions that you're working with, be able to schedule out task on a single, it allows you to scale out a lot easier without having to worry about many of the problems that are associated with things such as threading and multiprocessing and things like that. How many people have worked with async I/O? Show of hands. Okay, so there are a couple. I'll quickly go through some of these things just because I think that with this project that I've worked on, it's kind of good to know a little bit about. It introduces keywords async and await, which I'll go over in more detail, and it provides an interface for passing blocking work on an executor, which is very key for a lot of the work that I've been doing. Async declares a construct as a coroutine. How many people here know about coroutines? I'm guessing it's going to be the same set of, okay, some other people do. All right, so if you know anything about coroutines, it's a subroutine, well, very simply, a subroutine that can be paused at certain points and at certain point, it can be relinquished at certain points and will return you either a promise or a future object of which that will guarantee you a result. They run on the event, and for Python, it runs on the event loop as tasks that will publish its value to the object, as I said, and you can use it in many different ways. So you can define coroutine functions, you can define coroutine loops, and you can define coroutine context managers. So if you've ever opened up a file with blah 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 as with open blah 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 as da da da, kind of quickly going through it, you can do that in an asynchronous manner such that you're not blocking on that I/O for a long period of time if it's a large object that you're trying to open or work with. Await's kind of the partner in crime here, is the keyword that allows you to relinquish that control until the awaited coroutine that you've started completes. And it unwraps the future object, so you have the value. So in this way, you can have a lot of work going on simultaneously on one event thread. And anytime you reach a point where you think you're going to be waiting for something, it says, OK, I'm going to wait for this. I'm going to let something else start, right? And so those are the two kind of key things. I've got some simple examples here, kind of to get an understanding as to what's going on. I don't know if you guys, can you read that? OK. So in case you haven't seen it, very quickly, you import async I/O, and this is a very simple loop that has some form of waiting. You start up your loop, you run, and then you can run a coroutine until it finishes. Your run until complete, right there. And so what this will do is it'll wait for 5 seconds. If you want to do any other work in the meantime, you would normally be able to. In this example, there's only one coroutine that's running, so it's going to run it until it's finished, which is why it's run until complete. So if you see there is a sleep and some other things. A more interesting example, I create a bunch of different tasks that I want running. And in this example, there's multiple tasks they'll take different amounts of time to finish, even though I'm building them synchronously one by one. And so when you run something like this, as the program is going, when one task finishes, it'll say, oh, OK, this finished. Let me just grab that value. This next task finished. Let me grab that value. Or if I'm going to wait for a significant amount of time, I'll switch to something else and let that run for a while until it's done. Yeah. So that's kind of, Async IO was pretty big in the work that I was putting together. So I figured, based off of the talk, I kind of breezed through it a little quickly. But there's a list. You have a question?
Yeah. So with this, I know with threading, you're normally pinned to the same core.
Mm-hmm.
Some processes, it splits up multiple cores. What's the case with this?
So it's one thread. This is single thread, your event thread. So ideally, you push tasks onto that. And the idea is that, if I get a little bit more in detail, is that they're callbacks, right? So it's waiting for callbacks continuously. And when a callback happens, it just grabs that result and that task is finished. So
in other words, that you're still pinned to the same core.
yeah, you're still pinned to the same core. Now the difference here is that now you're making better use of that single core. So if you wanted to spread it out amongst multiple cores, you could do that more efficiently, ideally, with a multiprocess.
So if you want to spread it out among multiple cores, you just create a subprocess and then have
So now the other key thing that was critical to this project was Docker Py, which how many people here have used Docker? I've seen similar sets of hands. That's okay. That's okay. Docker is a container platform of which that you can isolate applications, isolate programs, services, or what have you. There's a lot of detail in how it does that, but ideally it's great for scaling out services because you can just as easily spin up something that's been baked. You can tear it down. It would take me a long time to go through that. So I definitely suggest that you go online, look up Docker, look up container communities, cloud native computing, which a lot of this stuff is kind of circled around, has a lot of great information about it. But Docker Py specifically, it's the API client for interacting with Docker, which is the container platform that I'm talking about. And with Docker, you create images that hold some form of logic, whether it's an application or you wrote some simple script that you want to be able to run quickly. The client allows you to create those images, it allows you to spin up images, it allows you to communicate with those images, and allows you to destroy, communicating with and destroying containers. So an image, when it starts, becomes a container. It can get a little fuzzy. Again, look at there's a lot of great information out there to play around with. Typically, it's very good for building out testing environments as well if you want to test things out. If you've got a Python 2.7, you want to try out Python 3, you can spin up a Python 3 container and play around with it and learn and understand without affecting your local environment. So it's definitely great for a lot of isolation style tasks and problems. It communicates, so continue on with Docker Py. It communicates over HTTP utilizing SSL certs. Hence, if you remember from the architecture, there are some certificates that I need in order to securely communicate to build out, to run a lot of those functions. But this wasn't built with Async IO. So you've got a situation where you might be waiting to start up a process. You might be waiting on input. You might be waiting until to figure out how many functions you have available in your action registry, your function registry. So Async IO kind of gives you a little leg up here, and this is great for whether you're doing something what I'm doing or anything else that you're kind of trying to build out event-driven code with products or packages or modules that weren't really built with that in mind. So run an executor. It's an interface for passing blocking functions onto executors to be run pseudo-asynchronously. So I say pseudo-asynchronously because the executor is either a thread pool or it's a processor pool. Thread pools, if you know anything about the GIL kind of does things where it's not very great for anything multi-threaded applications. But one thing that the GIL doesn't stop you from is, yeah, question?
What does GIL stand for?
Global Interpreter Lock. Sorry. So one of the things that the GIL doesn't really stop you from doing is threading when it comes to blocking I/O. So if you're trying to process a bunch of HTTP requests, threading actually works pretty well, right? But if you're doing a lot of high CPU intensive tasks, threading is very, 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 very bad. So processor pools end up being a great alternative to that. I'll just fork up a process, throw my blocking CPU call in there, and let that run, and then do a join when I know that I'm getting my information, right? The executor returns a future object, just like our coroutine when we run async and when we use async and await. So I can pretend that I'm still doing things asynchronously. There's a couple of caveats there that I had to worry about that I put out there. It doesn't really work at all with keyword arguments. So if anybody's heard of functools.partial, where you create partial functions, that's pretty much your saving grace for being able to use async IO for some of these things. So this is actually some code that is within my architecture. I don't know if are you able to read that very well? It's so-so, yeah, I figured as much. That's fine. Really, the primary thing that I wanted to highlight was that here I've got a Docker Py function, which is my inspect container, which lets me know if my function is currently running, and if so, get whatever input is in there and send it back to the person who triggered the event as like JSON or string or what have you. And that's running in the executor alongside of some of the other things. So that'll run. It'll give me the result that I need it when it's done, and then it passes it back to the user through the await function. I know it's kind of hard to see. I apologize for that. I can go through this really quickly. AOHTTP is built on top of Async IO. It's a great HTTP client server module. I like Flask, I like Django. I like this a lot more. It's very high level. It supports WebSocket signals and pluggable routing, just like a lot of the other ones do. You can build middleware for pre-processing and database connection setup, so you can actually pass your database through. I think some of the other ones do this as well. And you can either use the built-in runner, which is pretty good, or you can use Async IO compatible runners like GUnicorn and things like that. So all that cruft gone and understanding there, now I can finally tackle my action server. Very simply, 3 key pieces. I search for and spin up that function, as I had said before. I communicate with the platform to get information and data that's outputted from said functions. And then when the task is done, I destroy the function, right? I destroy the running container until the next time it's called up. So the 2 quick ways that they're communicated in for my RESTful call. So if I'm doing like a get, a post, a put, or a delete, you extract parameters from the request. I search for my action. If you're thinking about it from the model, the execution model, you start the action. You inject the parameters into the function as environment variables because it's a containerized environment. And then you retrieve the results from the function, and then you clean up, and then you return the data to the user. Relatively seamless. For WebSockets, it's slightly little differently. You search for your action, you start the action, and utilize standard input and standard output in order to grab the information from your running process, the function that's running. If input is sent to it, then it's sent in through standard in. If output is made, it comes out through standard out, similar to how you would write a terminal style application or what have you. Demoing this actually isn't too bad. My only worry is how is it going to look on the screen. So let's do this. All right. Are you able to see? You want to make it bigger? Yeah. OK, cool. So here I am in my platform. And if I do Docker service ls, it's going to list out that I've got my action server already running. Docker is pretty great for basic load balancing and things like that because, especially with the latest, with the new input, you get the routing for free when you build out a service. And that's also take a look at some of the document, look and understanding of how it works. It's really, really useful. But I've got my actor running, and if I do a images, you'll see 1, 2, 3, 4 images. I know there's others there, don't worry about those. But I've got 4 there that have serverless in the front. One of them is the actor, I know, but there are 3 others there that are primarily functions that have already been ingested, right, and ready for deployment and running. So what I can do is, let's do this. Oh, yeah, that's right. I can pull this in right here. And so this is my first example that I have here. I play a lot of Overwatch. I don't know how many people here play Overwatch. It's a pretty cool game by Blizzard. But one of the cool things about Overwatch is that in the community, Blizzard hasn't really made any APIs available like they do for some of the other games. But the community rallied around and they said, we're going to make our own API. We're going to scrape out their data and make it available to people to use. So a lot of competitive players, what they like to do is they like to look at that data and understand how well they're doing versus other people. That's a lot of talk for pretty much what I'm about to show here, which is I've got a Jupyter notebook that what it'll do is it'll connect to my serverless platform that I have hosted through Docker. It has a function there that grabs data on inputted user in Overwatch, so my username for this demo, and will then also look up the top 20 players for for either PlayStation, Xbox, or PC for a particular character that they play. And it'll do data cleansing, right? So it'll grab all the data, it'll compile all of it into something that's usable and readable readable to be utilized for my notebook, because I want to be able to look at and see how well I'm doing versus everybody else. So I can pull it up here. Some of the functions are simple, but a lot of people have more complicated. I need to be able to see this. So let me jump to it really quickly. Apologies. There we go. It's this one. So, and it'll probably be a little hard to see, but that's okay. Is that viewable by everybody? Okay, cool. So I've got a very, I guess you could say, relatively simple function here. Simple function here. Pretty much what I do is I go to the API. It goes to the API. It gets data as through JSON, but in order for me to get the top 20 players, I have to do some scraping. So I scrape one of the sites to figure out what the top 20 players are through using Beautiful Soup. So I go through the DOM, I pull out what I need, and then I clean up the data. I take, for each one of those, I ping the API and get their stats as well and compile it out. That way I've got a nice big JSON payload that I can then play around with. Yeah, payload. There you go. Overwatch show. So yeah, so I have this here. I ran it. I'm a big Diva player. I don't know who else plays, but I've already done the run because the internet's kind of been a bit janky around here. But I've done that run, so I've got the data. I can just as easily then should be able to print it out. I believe it says best stats. Just as easily run it. With data, there's a lot of data here. And that allows me to then get games played comparisons. So it looks like I'm not playing enough. Well, I'm out here. I don't have my PlayStation 4, so I'm not playing enough. And I can then perform analysis, and this is all Python code. I'll try to make this all available if you want to play around with it. It's kind of cool. One of the key things that I look at is final blows to elimination. So how many times am I finishing off the target? So I can see where I stand. I am very bad at this game, but I tend to stick around the objective. So that's pretty cool. Simple HTTP REST call to grab the data. It hits the serverless function that I've already instantiated. Here's another one. This one works on is that viewable? Okay, so this one is a WebSocket demo. So ideally, I have a chat where I put in a number and it does takes that number to a third power. It's very, very simple. So I can connect to it, which I've already connected, and I can show that I've connected to it because if I do this, RPS, you'll see that the top one here was started 11 seconds ago, and that's our function running right now, right? So I can just as easily say 10, and it gives me some output. I can do 50, and it gives me some output. Now, in case that's not believed, let's get the name, which is Tender Da Vinci. And you can see here that it's outputting the information as I run through it. So these are very simple examples, but they kind of show a lot of what's going on behind the scenes. And a lot of the serverless platforms do a lot of things like this. There's other there's export handlers and a bunch of other ways that are done, things that are done differently based off if you're on Lambda or on Google Function or Azure Function or OpenWhisk. But for the most part, I was able to successfully build out my very basic platform. Let's continue. Come on. There we go. So next steps. So there's a couple things that I didn't showcase because I'm still working on them right now. Function ingestion is one thing. So ideally, you want to be able to send the function to the provider and then be able to run that function, build out the proper image, and then make it available and ready for the user to call it so it spins up. That's one thing. Handling of function secrets. If you're connecting with a database, you don't want to send out very easily your database usernames and passwords. You need to have a secure cert database or cert store in order to handle those things. And then metering and monitoring hasn't been done, but I'm not trying to start a business with this. I think my superiors have already started figuring that stuff out. So with OpenWhisk, so that's something I might experiment with, but it's still something interesting to take a look at. The code's up and available on my GitHub if you want to play around with it. There's a lot of interesting things around. I'm still building them out as microservices, so if you follow or take watch, there'll be more things popping up around some of the next steps that I'm working on. And then to get a more in-depth knowledge on Async IO, because I don't feel like I've done it enough justice, definitely feel free to check this presentation out. It kind of gives you the lay of the land on what's out there, what's available, what do you want, what you need in order to get better with it. Crap. Okay, cool. That was weird. Yeah, so I'm Joir-dan. You can reach out to me on Twitter, or my email addresses are over there. I hope that I haven't bored you, and if I have, I apologize. If you have any questions, you can ask. If not, thank you very much. PSN? Oh, it's, I thought I showed it, Sakura-sen. So S-A-K-U-R-A and then S-E-N. S-A-K-U-R-A-S-E-N, yeah. If you want to play Overwatch too, yeah, feel free to hit me up on PlayStation Network. Any questions? Comments? Sorry if I bored you. All right, thank you very much.
just to rotate the program running. Then now, it's supposed to be launch.